Hello everyone, I'm Taira Shirahase and I'm from Okayama University. Today I will talk about high current performance analysis of a non-isolated high step-down DC-DC converter and miniaturization of the gate drive circuit. First, let me explain the background of this research. In recent years, with the rapid development of the information technology, the current demand by CPUs has been increasing. The power delivery system that is widely used in current data center is structured as follows. This system steps down 48 volt to 1 volt, which is required by the CPU through multiple stages of step-down converters. Because of the rapid development of information technology, this system is expected to have bigger power loss at the middle bus and need larger cables. Attention on this direct 48 volt to 1 volt conversion system has been gaining traction compared to current power supply system because it has lower power loss and allows the use of smaller cables. This system requires a new high step-down converter with these features. First, it must be compact because it is placed very close to the CPU and space is limited. Second, it must support a high step-down ratio, enabling direct conversion from 48 volt to 1 volt. Lastly, it must respond quickly to changes in load condition. Currently, many researchers are actively working on developing a new high step-down converter to meet these requirements. These converters can be mainly divided into two categories. The first one is isolated high step-down converters. Isolated converter use a transformer to achieve a high step-down ratio, so the circuit can be built with fewer components. However, because of the transformer, it is difficult to operate at high frequencies, above 1 MHz. Therefore, the response becomes slower and larger magnetic components and capacitors are needed, which makes it bulky. So the focus is shifted to the non-isolated converter, which is gaining attention as a promising POL converter. This type uses switched capacitor stages to achieve a high step-down ratio without transformer. Because no transformer is used, high-frequency operation is possible, allowing for fast response and small passive components. However, achieving a high step-down ratio requires many circuit elements, which makes it difficult to reduce the PCB size. Therefore, for data center applications, reducing the number of switched capacitor stages is necessary. In previous research, a high step-down converter with fewer switched capacitor stages was proposed. This converter improves the step-down ratio by combining a bidirectional Cockcroft-Walton circuit with a current doubler based on conventional design. However, there is a still challenge when applying this converter to data centers. The challenge is, as shown in this graph, it includes many floating switches, making power supply and isolation for gate driving difficult. But using isolated power ICs can solve this challenge. But it is bulky and take up a lot of space. Therefore, our research focuses on miniaturization of gate drive circuit. Here is an overview of today's presentation. The rest of the presentation will explain these points. Now, let's start by explaining the miniaturization of a gate drive circuit. For the miniaturization of the gate drive circuit, we use the cascade bootstrap circuit. This circuit is an extended version of the commonly used bootstrap circuit for driving floating switches. It is built by stacking multiple stages, And this circuit uses only small capacitors and diodes. So the gate drive circuit can be made very compact. In previous high step down converters, many stages were needed to achieve 48 volt to 1 volt conversion. Because of the forward voltage drop of the diode, the top level switch could not receive enough gate voltage. In the new high step down converter, the number of required switch to capacitor stages is reduced. As a result, all switches can receive sufficient gate voltage. Now, I will explain the operation of the cascade bootstrap circuit and the new high step down converter. This converter operates in 3 modes. In mode 1, SM1 and the odd number switches turn on. At this time, the main current path of this converter shown in red line, and charging current path for the bootstrap capacitors shown in blue line. And each bootstrap capacitor is charged from the capacitor one stage below. In mode 2, only SM1 and SM2 turned on. During this mode, the inductor current gradually decreased. In mode 3, SM1 and the even number switches turned on. At this time, the main current path of this converter shown in red line, and charging current path for the bootstrap capacitors shown in blue line. As you can see from these operation modes, this converter operates similarly to a buck converter. This is a new high step down converter we have built. It has 3 switch to capacitor stages and uses a cascade bootstrap circuit. The size of the prototype board is 61 mm by 73 mm, and the height is 6 mm. The yellow area in the picture shows the gate drive circuit. As you can see in the picture, it is significantly smaller compared to the one isolate power IC. And we carried out the experiment under these conditions. First, we conducted an experiment to verify whether the cascade bootstrap circuit works as expected in this new high step down converter. This graph shows the gate source voltage waveform of S1 to S7 when the output current is 70 ampere. As expected, each gate source voltage drops slightly due to the forward voltage of the diode, and all switches can receive sufficient gate voltage. Then we conducted experiments to identify the causes of efficiency degradation under high current conditions. This graph shows the efficiency when the output voltage is fixed at 1 volt and the output current is varied. The efficiency is 86% at 30 ampere and decreases significantly as the output current increases, reaching 68% at 90 ampere. This graph shows the result of the loss analysis. This graph shows the main losses come from dead time and PCB wiring resistance. These losses are similar to the losses in buck converter. This loss is unique to switch to capacitor converters, but the loss analysis shows it is small. Most of the total loss comes from the PCB design. The loss happens because a large current flows through vias between the top and bottom of the board in prototype board. But this problem can be improved by using a design with lower wiring resistance. So the new high step down converter is expected to have the same or better efficiency than the current power supply system. This is conclusion. In this research, we focused on the miniaturization of gate drive circuit. As a result, we were able to significantly reduce the size of the gate drive circuit by applying a cascade bootstrap circuit, compared to using an isolated power IC. Also, the control circuit area on the PCB board is still large. Faster miniaturization is possible by integrating these circuits. The cascade bootstrap circuit worked as expected, even under high current conditions. And we also found that efficiency can be improved by optimizing the dead time and redesigning and the PCB to reduce the wiring resistance. And loss analysis shows a new high step down converter has equal or better efficiency than the current power supply system. These results show that the proposed new high step down converter has promising performance as a 48V to 1V POL converter. Thank you for listening.